Good morning, everybody. Well, I guess it's afternoon in some places. Welcome to the Stats for the Masses webinar, Power Analysis, a brief yet useful overview. My name's Elaine Eisenbeisz. I'm the owner and principal statistician here at Omega Statistics. We've had a large number of registrants for this presentation, so I see many re-attending with us today, so thanks for taking the time to join us live. Today I'm going to present an overview of a priori power analysis. A priori techniques are used when you design a study, and you use them in order to determine your best sample size. And that's once you start figuring out what you want to do with your study, start figuring out, what you're going to test. Your first question usually is, well, how big of a sample do I need? Is it even possible to do the tests I want to do? Am I going to be able to get enough people? So today's just an overview, but I do hope that the information you receive today will give you some ideas and guidance on designing your own studies. I say it in all the webinars, use what you learned today, apply it in a holistic way. Power analysis is part of the big picture of a study's design. I guess I should make sure everybody can hear me okay. If you can just type in really quick in the question area or the chat area. I'm on my own today, so I'm trying to figure it all out. But if you can just somebody let me know. Good. Awesome. Thank you, Jesse. So great. The presentation is going to last about 40 to 45 minutes, and then we'll take some time at the end to answer some questions. I'm also going to try to answer some as I go through things. So we'll do that. Some bookkeeping, some housekeeping info. I currently muted the line, so you can only hear me. Our board operator is not available today, so it's just me here. So I'm going to try to remember to take some time as I go through the presentation to pause and ask for questions from the audience. So type questions you have on the chat board or in the question area there. Bear with me. I'm not the most tech savvy person when it comes to GoToWebinar, but I'm going to do my best. And if it doesn't work, maybe at the end, then we'll try to catch them all. If you have any technical issues, I often find that just logging out and back into the webinar clears up just about everything. So when in doubt, just reboot. All right, so let's get started on our slides. First, I always like to show the slide to tell you a little bit about Omega Statistics. We have Omega Statistics, and this is part of our Stats for the Masses webinar series. And I also do live seminars. So the webinars, I try to keep them free, and hopefully you find them useful, and it just maybe gives you a little bit of ideas as you're getting ready to start looking into things a little bit more deeply. Statistics can be difficult. It's a difficult subject for even seasoned researchers. Often your textbooks, classes, training programs, they make things a little bit more confusing. So my goal with Stats for the Masses series and for Omega Statistics as a company is to inform and educate everybody about statistical concepts. And I try to put it in layman's terms whenever possible. Sometimes that isn't easy, but I try to do my best so everyone can see the elegance and usefulness of statistics. I personally love statistics, and I like to share that, share the love. The webinars are always free, and I do record them. So if you can't make it to the live meeting, you can view the webinar later at your convenience. Also, you can go to the webinar page of the Omega Statistics website and look at any of the past ones that we've done. Our next webinar will be in May, and I'm not exactly sure what I'm going to cover next. I'll send an email in a week or so to announce it, and then I'll provide a link to sign up. So stay tuned. And of course, let me know if you have any suggestions. I'm open to hearing ideas. So here's some things that we do in Omega Statistics, and most of you that have been here before for the other webinars have seen these slides. I am a private practice statistician, and so this is what I do. And I do medical and clinical research, biotech, epidemiology, things like that. I also help with journal articles, researchers who are writing their journal articles, predictive modeling, dissertation assistance. Probably about 50% of my business is clinical, another 40% or so is dissertation, and maybe 10% is just miscellaneous things. They say the nice thing about being a statistician is you get to play in everybody's backyard. I can design a survey if you want, and I'll work on projects just about any size, small to very large. Our motto is to provide elegant solutions effectively applied. So let's get started. What is power analysis? Well, I always like to do this where I get a textbook definition and then I kind of try to make it simpler. The textbook says the power of an experiment that you are about to carry out quantifies the chance that you will correctly reject the null hypothesis if some alternative hypothesis is really true. That's very confusing. So the stats for the masses way of thinking is I try to think of power as a flashlight. And significance is maybe hiding in the corner of a room. So you need a flashlight that's really powerful enough to see that significance that's really there. If you don't have enough power, you're not going to see the significance. So a power basically of a study means that if it is true that there is a difference, a true difference in the population that you're sampling from, you want to be able to see it. You want to have a big enough sample so that you can see that difference. So, that's what we're going to try to talk about more here. There's two main types of power analysis. There are other ones. There's compromise power analysis and such, but I'm not going to go into that too much today. The two main ones are the a priori and the post hoc. A priori means before. Okay, so it's something that we do before we conduct our study, and we do this to determine our best sample size. This is the type of power analysis used by most researchers. This is the one that you're going to really care about. How big of a sample am I going to need? Post hoc power analysis is performed after your study. Often, well, hopefully not too often, but sometimes you will run your study and you won't have any significance. Nothing shows significant. So what you might want to do then is do a post hoc power analysis where you look to make sure that did you have a big enough sample to see the difference that you found. Maybe you didn't find a big enough difference. Maybe you were maybe it was like a 2-point difference and your power is only studied for a 5-point difference between two groups. Well, if you didn't have a big enough sample to see that 2-point difference, you won't see it. So basically, was the flashlight strong enough? Okay. Many researchers and statisticians frown upon the post hoc. However, because it's based on sample characteristics, basically you're just taking the information in the sample that you pulled and using that to see how good your power was. And what if your sample wasn't, what if it was biased? What if it wasn't pooled quite right? You're using information that might not be very good to make some conclusions. Also, you're not using your population, you're using just the sample you pulled. So there's arguments for and against it. But in this webinar, we're going to look at the a priori techniques. So we want to know our sample size. So here's what we'll need. We need to know what's our significance criterion. Most studies set a 95% level. Okay, what that means alpha, this little thing right here, this is your alpha, and you want to set that at 0.05. And that's your probability allowed for your type 1 error. Type 1 error, that's whenever there's truly, you're saying basically there's truly not any difference, but you're saying there is. You somehow found significant results when in truth they weren't really significant. So with alpha 0.05, you're going to allow yourself to make that error 1 in 20 times. 5 divided by 100 is 1 in 20 times. So it is possible. I mean, we deal with probability in statistics. It's not empirical. It's not 2 plus 2 equals 4. We're guessing that it's maybe 2, and maybe the other number's kind of 2, and so we're thinking it's kind of 4. So when you deal with these probabilities, it's not like the 2 plus 2 equals 4. We always have that error, right? We're always allowing for us to be wrong because we have the probabilities because we're pulling a sample out of a population. If we knew the truth in the whole population, we wouldn't need to sample it. So alpha of a 0.05 is usually what we will use. Power is not the same as the probability of a type 2 error. Type 2 error is beta. It's this little value here. Power is 1 minus beta. So many a priori power analyses are set at 80% power. So that means you want to give yourself an 80% chance of seeing significance if it's really there, to see that difference. If you're, like I said, if you're looking for a 5-point difference, you want to give yourself an 80% chance of seeing that 5-point difference. Sometimes you'll see a little bit higher. We're going to be working with GPower software today. It's free, downloadable, and you can play with that. And look at your power, it always has a default of 0.95, which is 95%. Well, that's just way too powerful. And of course, the more power you're asking for, the bigger your sample size is going to be. So it's all about the give and take. So usually we'll set our alpha at 0.05 and we'll set our power at 80%. The big things we don't really know, though, are our effect size and our sample size. So our effect size is very important to figure the power. And this is where a lot of people get hung up. We need to know how large of an effect do we want to see. Is it a 5-point difference? Is it a 10-point difference? Is it 20% between two groups? It really depends on what you're testing for and what you're looking for. So how big of a difference between groups, how strong of an association, for instance, in a correlation, how strong of a correlation are we looking for? We need to know how large of an effect would be considered significant to us clinically. Maybe, and then we're going to try to make it statistically significant. Sample size, of course, is what we're looking for. Okay, how large of a sample do we need to detect that size of an effect? I'm not seeing any questions pop up on the question board, so I hope I'm seeing the questions. I don't see any, so I guess I could stop now and ask if there's any questions yet. Maybe we're too early on in, but I do not see any. Oh, no, okay. Well, at least Jesse's saying no and yes. Thank you, Jesse. A priori power analysis. We need 4 things, okay? A useful mnemonic is BEAN. And it helps you to remember these 4 items that I kind of just went through on the previous slide. There's beta error, which is that type 2 error where power is 1 minus beta, okay? And so we're going to need that beta so we can subtract it from 1 to get our power, okay? Effect size, we need to know that. And usually the researcher will tell us what the effect size is, or we will know from literature. Maybe we've looked at the literature, and it'll kind of give us an idea of how big of a difference, you know, things like that that we're looking for. It could be something to do with your, you know, what kind of test you're using and what you want clinically to be a big difference. And we'll go over some examples. There's also the alpha error rate, which is that 0.05 I was talking about. You know, how often, how much are you going to allow yourself to be wrong and say you found significance when maybe it really wasn't there? And then, of course, sample size. And as is the way in mathematical formulas, if you have 3 of the items, you can get the 4th one, right? Paul's asked, what is meant by overpowering? Overpowering is whenever you pull such a large sample size that you're going to see significance on everything. A consequence, and he also asked, what's the consequence of that? Well, you know, it's all about time and money. So if you are pulling, if you want to pull a sample of 10,000 records, sure, you'll see significance on everything. But I mean, really, if you're going to find a significant difference of 2 points or 1 point or half a point as significant, and you have 10,000 records, that's not really necessary. It costs a lot of money to pull a sample, especially in clinical research. A lot of people use SurveyMonkey and such. That's not so bad if you're doing that kind of a research where you're having people fill out surveys on SurveyMonkey and you have the whole world there to do that. But, you know, it does take time. Sometimes you want 100 people and it's like pulling teeth. You get 90 and that last 10, it's so hard to get them, and you'll get 90 in 1 month and then you'll take another 3 months to get that last 10. So, yes, it would be great if you could go out and pull the big, huge sample and you'd see significance everywhere. That's where statistics can break down, and that's how some people try to cheat it. Because they'll say, well, I'll just pull a huge sample and then everything will be significant, and that means that my findings are meaningful. Well, you have to think about what's meaningful first and then try to power your study accordingly. And that's what overpowering is. It's just too powerful, and you're going to see significance everywhere, even on the tiniest effects that don't matter. Okay. Did I answer that for you, Paul, well enough? Kind of fun looking at the message board. Okay, so what you have for an a priori power analysis is we do have 2 things that we know. We're going to say that we know. Okay, we can set a 95% level of significance as a criterion. What that means, our alpha is going to be 0.05. Boom, we got that. We got the A, right? Out of being, we got the A. Power, we got our B too. Let's say our betas, we're going to make that 20%. We're going to subtract it from 1. That leaves us with a power of 80%. And these, like I said, are usually the defaults. These are what most people use, an alpha of 0.05 and the power of 80. Okay, so we have those two. What we don't have yet are the effect size and, of course, the sample size. So what we really need to get this equation going is the effect size so that we can figure out what the sample size is. I said a little bit earlier, usually an effect size is determined by the researcher. So if you're a statistician, you're going to ask your researcher, how large of a difference do you consider to be significant? Or how strong of a relationship between the variables do you think would be considered significant? If you're a researcher, then your knowledge, maybe some previous study you've done, or some that your colleagues have done, or a review of the literature, requirements from your sponsor, or you might say, well, there's a drug out in the market now that's 20% effective. We want something that's 25% effective, so or 30%. So you kind of need to know, what you're dealing with there. A lot of times I'll ask a researcher, how big of an effect are you looking for? How big of a difference? Sometimes they don't know. And I usually direct them to go back and look at the literature or come up with some kind of an idea, maybe discuss it with them, or maybe even run a power analysis on a couple different scenarios. What I'm going to show you today in the GPower is very simple kind of power analyses for some rather simple tests. A lot of studies get very complicated, and a power analysis is basically done in pieces. Okay, we have this part for this test that we're doing, and then we're going to run this power analysis for this other test. What's our primary endpoint? That's going to matter the most. So there's a lot of give and take, and a lot of, we actually do power studies where we will throw in some different numbers and kind of try to settle on something that's going to answer most of our questions for the sample size, maybe not all of them. And of course, what's the most important, right? What's the most important endpoint? Let's see. Indu's asking, can the effect size be maybe a 5-point difference in average sales between two groups like control and test? Yes, it can. It can be dollar difference. Yes, you're doing any kind of test you can think of. There's a power analysis for it. Absolutely. And I'm going to show you some formulas, and then you'll see. But yes, it's not just one formula. First, you need to know what your research question is. What am I doing? Am I looking for a difference in averages? Am I looking at correlation coefficients? Am I looking at maybe predictors in a regression model? How am I setting up my study? Then you want to determine your power with formulas and effect sizes that match the test you're using. So, yeah. You can do any kind of you can do power analysis for just about any kind of test. Sometimes they get a little strange, and like I said, sometimes you have to piece them together, but it is doable. So an effect size, according to Wikipedia, in statistics, an effect size is a measure of the strength of a phenomenon. So, for instance, a mean difference, a correlation, logistic regression, maybe it's your odds ratio. That's an effect size. The p-value tells us if the effect is significant. So you might get a p-value of 0.04, and you set your alpha at 0.05. So you're saying, oh, yay, I have statistical significance. But it doesn't tell you how good it is, right? If you have a p-value of 0.04 versus a p-value of 0.01, that doesn't mean that the 0.01 is better, because you're just setting your level of significance. You set your alpha at 0.05. So anything less than 0.05 is going to be considered statistically significant. And there's no degree in that. It doesn't matter if it's 0.01, 0.0005, whatever your p-value is, you only care that it's less than 0.05. An effect size will tell you how big of a difference or how big of an effect you see. That's what matters. So an effect size could be your mean difference. An effect size could be, like I said, your correlation coefficient. Do you have a correlation of 0.1, which is like very small, or is your correlation 0.7, which is very strong? So that's your effect size, and that tells you how big of an effect you have. Okay, not the p-value. So there's many ways to compute a desired effect size depending on the test that you're planning, okay? And here's some, like I talked about before, mean difference. t-test, analysis of variance. I'll show you how to do those today in GPower. I'm also going to show you how to do a Pearson's correlation to find a power for that, the sample size for that, and a regression, a multiple regression. I think Indu asked about that. She wanted a multiple regression, so we'll look at that today. How do we find the effect size? Yes, this is the fun part. I say here, bear with me on this. It does get better. We're not going to do any formulas today. We're actually going to use the software that does it for us. That's the nice thing nowadays. Computers are wonderful things, so we don't have to do a lot of the calculations. So we could use the formulas though. These formulas and a lot of the effect sizes that I'm going to just be throwing out at you today are from Jacob Cohen. He had a power primer. This is the end all be all on power. And it was 1992, so it's been around a while, but everybody still uses Cohen. He uses Cohen's D for independent samples t-tests, and here's you're just subtracting the means, one mean from the other, and you're dividing it by your standard deviation here, and hopefully they have the same standard deviation. If they have different standard deviations, then it gets a little more complicated, but there are formulas. And here's a formula for a one-way analysis of variance. Okay, again, we are subtracting the two means. Now we're squaring them, then we're summing them up, and then we're going to sum them up from here, and then we're going to take the number of groups, and then we're going to take the variance, and so the variance of the error. So it gets really crazy. You won't have to do this today. Then there's they get even crazier. And it even gets crazier than this, but this is the correlation coefficient. Actually, this looks a lot more complicated than it really is when you start plugging in the numbers. However, this would be the formula you'd use, and your effect size is going to be this R. This is your correlation coefficient. This is our statistical notation. Okay, for a correlation coefficient. But I said, don't worry, we're not going to be computing any of these today. I just kind of wanted you to see that there's different formulas, and there's probably thousands, maybe tens of thousands of formulas, depending on what you're looking at. Okay, so Paul had another question. Doesn't a smaller p-value indicate more confidence when you have the observed results? P equals 0.05 means was it perhaps 1 in 20 due to chance versus 1 to 1,000 due to chance with a p of 0.001. Yeah, that's true in real life and what you're looking at. Yes, absolutely. Your probability, because your p-value is a way of looking at a p-value is like, wow, what's the odds of seeing that difference? If there was no difference, right? What are the odds of seeing a mean difference of 5 points if there truly wasn't a difference between the groups? So of course, your probability of 5% versus 0.1% is going to be, they are different, yes, and one is a much lower probability. However, whenever you set up your study, you're just setting it at a point. You're just going to say that anything less than a 0.05 or whatever level you set is going to be significant. So in theory, you're not supposed to say highly significant or very, very significant. You just say significant or not. So it's just the way we do it. But you are right. Yes, a p-value of 0.001 absolutely is less than 0.05 because it's a probability. Yeah. But if we set it at 0.05 for our test, that's all we care about. Is it lower? But even if it's a 0.05 versus a 0.001, that doesn't tell you how big the size of your effect is, right? It just tells you, wow, what are the odds of seeing that? If there was no difference, what's the odds of seeing that? What I saw. Yeah, so that would be the difference in that. So researchers into behavioral and social sciences or working on their dissertations usually use Cohen. However, instead of computing formulas, they make rules of thumb, use of these rules of thumb. And I have a little table I put in a little bit later too. But these rules of thumb help you in determining a sample size. A lot of times if a researcher just doesn't know or just can't find it, they will go with this, okay? And Cohen, he put a lot of different criteria together for different tests. So Cohen's D would be your t-test. Cohen's F is going to be your ANOVAs, okay, or any kind of that kind of group comparisons when it's not a t-test. T-test is 2 groups. ANOVAs are more than 2 groups. And then you have your R, which is your correlation coefficient. But he took all these different kinds of effect sizes and then he put limits on them, thresholds, what's small, what's medium, what's large. So the larger the effect, the smaller sample you're going to need. Because if you want to see some teeny tiny effect, like a small effect of a 0.20 on a t-test, that means that you're looking, say, maybe for a 2-point difference. Okay, but I wouldn't know until I figured it out, but you're looking for a smaller difference. Well, to see those differences, you're going to need a bigger sample size. An example I kind of use is that you want to know how many redheads there are in a population. So you go out and you pick a sample, you pick 3 people. Just by luck, you got a blonde, a brunette, and a redhead in your sample. You have a sample of 3. So you're going to go, wow, well, there's no difference there. 33%. 33% blonde, 33% brunette, 33% redheads in the population. So redheads aren't rare. Okay, now go out and pull a sample of 100. Now you might start seeing that there's not as many redheads unless you just, somehow by chance pulled a strange sample again. But if you're randomly pooling from the population, you should be getting an estimate of what is true in the population. Now, if you go out and you pull 1,000 people, that's more information. 10,000. The more you pull, the more information you have. Okay, and that's why if you're looking for a small effect, you're going to really need to pull a larger sample. So a lot of people go with these medium conventions, right? They'll go, okay, I'm going to do a t-test and I'm going to go for a medium effect, which is a Cohen's d of 0.5, and then you'll power it accordingly. If you're doing a clinical research, though, like I was saying, if you're comparing your new drug to a drug that's in use, you know that you have to have a certain proportion or certain percentage better difference in order to even go to market, right? Nobody's going to care if your drug is 1% better. And people might care, but are you really going to want to run a whole study and pay millions of dollars for a 1% difference? No. So what you want to do is say, well, what's the minimum difference that I think matters, and empower your study accordingly, and use formulas or some kind of computations, or call your trusty statistician to run some power analyses for you. So I guess the next question would be, what would be the difference? What is small, medium, and large? Well, according to Cohen, he said a small effect, it's real, but it's difficult to detect because it's rather small. An example would be differences in weight between 2-year-olds and 26-month-olds, right? That's only a 2-month difference between the kids, the 2 groups. So you probably might not see much of a difference. So if you want to call something difference, like a 2-pound difference, or something like that, you're going to need a bigger sample size to see that small effect. A medium effect is large enough to be visible to the naked eye. So differences in weights between 3-year-olds and 5-year-olds, you can see they're different. They're taller. The 5-year-olds are taller and they weigh more. Okay, so you can see it. A large effect would be grossly perceptible and therefore large. So differences in weights between 1st graders and 6th graders. Obviously, every 6th grader is probably going to be much, much heavier than a 1st grader and taller, right? So that kind of, you can think of it that way. So the smaller the effect, the larger your sample size is going to need to be. Let me see here. I have another. Do you have the formula for 2 groups where the variance is different? I can find that and send that later for you, Indu. And I can maybe, what I'm going to do is, I didn't get to the R and SAS code today to show you. So we're going to work on GPower. And then what I'll do is I'll send some handouts. So I'll try to maybe put some of these formulas in, or a link or a reference to them. But basically the bottom, the denominator is just going to have the 2, they're going to be pooled. And I'll send something on that for you. So I made a little table here too, and it's again, it's kind of what I showed you a couple slides ago, but here's our effect sizes. Here's small, medium, and large. Here's our different effects. Here's Cohen's d. Here's partial eta squared, and there's eta by itself, and depending on the type of design you're using, you might use one or the other. Correlation, you could use an R squared, or you can use the R. These are your correlation coefficients here, and your R here. Multiple regression, you can use the big R squared or the R, and so they're basically the same, except for with the multiple regression, you have a lot of predictors. So it's not comparing, a correlation is comparing one variable to another variable, but a multiple regression is a lot of predictors more than one predictor, two or more, on some kind of outcome. So it's the same kind of convention. However, you just have more in the computations. And then there's chi-square goodness of fit, which is a W. Sometimes you'll see a phi. But these are all your different effect sizes. So these are very useful, especially if you're using GPower, or you're just trying to just get a little estimate, like a little guess at what you might need. A lot of people will do a feasibility study. Is it even feasible? Should I even be doing this? Is my sample size going to be so prohibitively big that I can't even do the study? A lot of times I'll get people they'll say, well, I heard 30 per group is good, so I just put in 30 a group, but then they want to see a very small difference, and they're not going to. You always want to kind of check your sample size first. Make sure it's something that's even realistic for you to do. All right, so let's use some of the information we have to compute some sample sizes. Here's a free software, is GPower. You can download it from this address here. Okay, so I have my notes, and I'm going to pull up GPower, and I'm going to do my best to go through these and ask questions as I go through, and I'll try to answer them. Okay, and we'll just work some of these together. So let me go ahead and pull up my GPower. Alrighty, so GPower, there's different ways of doing it. Remember I said there was the a priori, there's the post hoc. So right here, you can get all these different types of power analysis in GPower. So here's the one we're going to use today, because we're going to look for the sample size. There's also the compromised one, where it's kind of a little give and take. The criterion, I don't think I've ever used that one. Post hoc is the one I talked about whenever you don't get significance and you go, gee, did I even have a big enough sample? And then there's a sensitivity analysis, which I don't use too much either. Typically, I'll use this a priori and this post hoc. Really don't ask me to explain these other ones, because I never really use them too much. So what we're going to do is we're going to keep it on a priori today. Okay, so the first one I'm going to show you is a t-test. Okay, t-test means you have two groups and you have one outcome. Okay, so one dependent variable and one independent variable with two groups. So maybe you're comparing genders on test scores. Maybe you're comparing to, two other types of groups, maybe two classrooms on something, some test scores, or I don't know, I have test scores in my head today, or treatment and control group. Okay, if you're in clinical research, you have a treatment group, you have your control group, and you have an outcome. Okay, improvement, something like that. Well, it wouldn't really probably be improvement. It'd be some kind of score, something you can get an average on. Okay, because they're means for a t-test and ANOVA. You have means. Okay, so we're going to take t-test, and then we're going to go into our statistical tests and look at all the different ones you have. You have so many different things you can look at. It's very nice. But we're going to go down to the mean difference between two independent means. So this one here, the two groups. Okay. A priori. Now you can have a one-tailed test or a two-tailed test. A two-tailed test means that you're just looking for a difference. You don't care about the direction. You don't care if treatment's bigger than control or control is bigger than treatment. You just care if there's a difference between treatment and control, for instance. Sometimes, though, you might want your treatment to be better, over the control group. Then you would do a one-tailed test, and I'll show you the difference. A two-tailed test always needs more of a sample than a one-tailed test, but you need to say if you're using a one-tailed test early on. It's not fair to run your numbers, get a p-value that's like 0.08 that wouldn't be significant on a two-tailed, and then go, oh no, I meant to do a one-tailed, and make it a 0.04. You can't do that. You should always say beforehand whether you're looking for just the difference or if you're looking for an improvement of one group over the other. Okay. So usually when you hover over this effect size, it'll tell you. It gets kind of tricky. I don't know why, but sometimes it'll say right here, if you hover over it, see, it's not doing it now. If you hover over it, sometimes it'll tell you what the different effect sizes are, and then you can just choose it, okay? But I'm going to choose an effect size of 0.05, or 0.5. Oh, there, see, I hovered over it. But it's really, it doesn't want to do it all the time. But see right here, I hover over the effect size, and GPower's nice enough to say, well, small's 0.2, medium's 0.5, and 0.8 is large. So I'm going to choose 0.5, Okay. The error, I like 0.05. That's usually the standard. GPower always gives you a default of 0.95. I like 80% power. That's more than enough. This allocation ratio is group 2 to group 1. I'm going to say equal groups. If they're equal, that means your ratio is going to be 1. Sometimes maybe you have twice as many in one group as the other, right? So your ratio might change. But let's just say we're going to have equal groups. Most of the time we would. And then all you do is hit calculate. And there you go. It tells you right here how much your total sample size is needed, which is 128. And you need 64 in group 1 and 64 in group 2. Okay. And these are little criteria that it tells you. These are interesting, however, not really important for you to really understand. But I have a two-tail test here. So what I have is I have a critical value, which is whenever you do a test, you have a test statistic. In this case, it's a t-test. So what we're saying is if you get a critical t-test score, a t-value of greater than 1.97897, then that means you're going to have significance. Anything less than that, you're not going to have significance. Right here is our alpha divided. This is actually the 0.05 divided by 2 because we have in our normal distribution 2 tails. You could be greater, you could be lesser, right? So we're allowing that they're just different. Okay, so to do that, we have a 2-tailed test. This right here is our beta, which is the 20%. And up here is our power under the dotted line here. This gray right area up here under here is how much our power would be, which if you look at this, that's about 80%, right? So if you change this around a little bit, let's say I wanted the power of, let's say I wanted a 1-tailed test. So I'll do that and I'll calculate it. Now see, I only have 1 green bar. And see, now I only have to beat a t-score of 1.66. So I'm going to see significance a lot easier because now look how big. This doubled because now we don't have anything over here. Okay, so now we can do it that way. So if we look at maybe now let's make our power, let's say we want to power 50%. Okay, and now we still have a 1-tailed test. So right up here is our power. So this means right here, we could have this B right here is our type 2 error, right? So we're going to miss significance half of the time, even if it's really there. So they're interesting, and you can kind of Google things, Google GPower graphs, and you can read more about it. But what we want is we want this to be as small as possible. So we don't want a 50-50 chance. I want to have 80% chance of seeing significance that's there. So this is where I might be missing it. So I want this part to be much bigger. Okay. If you click up here on the protocol, it actually gives you a nice little printout. You can save it, you can print it, you can put it in your report as an appendix. So yeah. So that's for a t-test. Oh, and here right down here, it shows you how much power you got. See right here with a 1-tailed test, even though we kept all the criteria the same, now we only need 102, 51 a group, because we have a 1-tailed test. Okay, it's going to be easier to see our significance with 1 tail. Do we have any question on the t-test? Okay. What I'm going to do then is go into an ANOVA. Okay, let's do ANOVAs. Okay, so what we want to do, let's see, I'm going to compare 3 groups of students, okay, and it's going to be on a math test. Okay, so now we don't have a t-test anymore because now we have 3 groups. Okay, so to do this, we are going to go into F tests because an ANOVA uses an F statistic. Okay, then we'll go over here and we're going to choose fixed effects, omnibus, one way. Okay, and again, there's so many different ones. You can have your repeated measures tests, between groups, repeated measures within groups, within and between where it has the interaction. You have MANOVAs down here. You have some regressions. We'll look at that in a minute. But there's so many different ones. But we're just going to look at a straight between groups ANOVA. Our main effects would be, are there differences between the 3 groups? Okay. So, oh no, we're not. We're doing the omnibus one way. Sorry about that. Okay, ANOVA, fixed effects, omnibus, one way. And we're doing a priori again. Okay, so this time I'm going to set it at 05 again. I'm going to make this 80 again because I don't like that 95 is too big. Okay, now our effect size, again, you hover over it. I did it for a minute. You hover over it and it'll tell you. There we go. Okay, so small is a 0.1, medium is 0.25, large is a 0.4. Okay, so I'll just say, let's do 0.25, the medium. Okay, now I can just calculate it. And now I need 200. Oh, wait, I said 5 groups. I need 3 groups, right? Didn't I say there were 3? So now I need 3 groups. So there we go, 159 for the total sample size. Okay, so that means in the 3 groups, you're going to divide them up. Okay, and hopefully 159, I think it is, divided by 3. So you're going to need 53 people in each group. Okay, what is the non-centrality parameter? That's a good question. I'm not exactly sure. I can find out and let you know. It has, it does have, it's lambda, but I'm not exactly sure what it is. But I'll make a note and I'll try to answer that. A lot of times you'll see there's way more information than you'll ever need to use. A lot of times I'll do statistical tests and I'll get 50 pages, 100 pages of output. And I certainly don't need all that information for my reporting, but it'll give you more than you ever need. I'm an applied statistician, so I look at what I need, knowing what I know, and I kind of, I'm not into the big, heavy theory of it. So I don't do too much of that. Omnibus. Indu wants to know what omnibus means. Omnibus means overall. Okay, so a lot of times when you're doing an ANOVA, a t-test, okay, for instance, a t-test is just 2 groups. So when you run your test and you get significance, you go, okay, one group's different than the other. And you can look at the means and go, okay, group 2 was higher, significantly higher than group 1, or group 1 was significantly higher than group 2. When you have more than 2 groups, the omnibus test is your ANOVA test. What it's testing for is there any difference between any pairs on those 3 groups? So is group 1 could be different than group 3, group 2 could be different than group 3, group 2 could be different than group 1. They could all be different from each other, right? But we don't know. The omnibus test is something you do first to just see if there's any kind of differences at all between any of your groups. Then if there are differences and you get that significant value, you get a p-value of less than 0.05, that allows you to run more tests, which are called post hoc tests. And that's when you start comparing your groups. Then you go, okay, where are those differences? I know there's a difference somewhere, but where is it? So your omnibus test is when you have an ANOVA, MANOVA 2, a lot of tests where you have more than that 2 group, or it's just a straight, I need to see 2 different, differences between 2 groups. You need to do that omnibus test first, just to see if there's any kind of difference at all. Does that make sense, Indu? Okay. Okay, so let's say we don't really know what, maybe we don't really know what our effect size is, but we have some information. Okay, let's say we know some means and the means and the sizes of some groups. Okay, we have 3 groups. Maybe we have the standard deviation with each group. Let's say we have 10. Okay, something like that. Then we can kind of look and see maybe if there is, calculating some of these different effect sizes using some information that we might know from the literature or something like that. So let's see, I have number of groups 3, standard deviation with each group 10. So let's say we're going to have 100 for the mean of group 1. And then we want to, for group 3, 105. And let's say we'll make the mean for group 2 anywhere between 100 and 105. Let's say about 102.5. We'll just put it right in the middle. Okay. So this is going to result in a larger value for n than any other choice, because this way we're allowing for these 2. This is going to be your bigger difference here between the 1 and the 3. Okay. So let's see. Let's look at calculating it. So right there is my effect size. It's going to be 0.2, which is a little smaller than my 0.25. Okay. So I'm going to just transfer it over here. So it transfers it right over. Boom, boom. I still have my 3 groups. Everything here stays the same. I'm going to calculate it. now my sample size went up. Okay, because now I have a little bit smaller of an effect size. If I wanted to say an effect size of 10, it's going to go way up. Now I need almost 1,000 records. Okay, so the smaller your effect, the more sample you're going to need. Let's say I want a bigger effect size. What was it? 0.4 is my large. Oh, good. Now I only need 66. Right? So you really want to think about how big of a difference that effect size really, really matters. Okay. Any questions on the ANOVA? Oh, Henry wants to know if the control groups counts as a group. Yes, it does. Because any group that you're comparing, you have to count it, right? So your control group, if you're comparing treatment to a control, you have those two means. So yes, it does count as a group. Okay, so any other questions on the ANOVA for now? We got through 2. I got 4 more. Okay, let's do correlation. Oh, Indu wants to know about other. Which one? Indu, is there a certain one you want to look at? Repeated measures. Okay, let's look at this. Repeated measures between factors. Okay, so now what we're doing here is we're looking, say it's 3 groups of people. Okay, and well, let me see, which one here do I want to use? I'm trying to think. Let's do within factors. This actually, you could have one group and look at it over 3 time periods. Okay, it's kind of similar to a paired t-test. You have like a before and after measurement. So it's the same group of people, but they're being there may be a pre-test and post-test. A repeated measures ANOVA style is now you have more than 2 test times. Maybe you have a pre-test, a midterm test, a post-test. Maybe you have 4 or 5 different measurements, times. Maybe you're looking at 10 different times. So again, you want to use this whenever you're having, and you're looking at within groups. So basically when you're within factors, you're saying, I have this one group that I'm looking at over time. Do their scores change on your test from pre to mid to post, right? You have 3 test times. Are their scores changing? So we would have our effect size here. I'm using 0.25. Let's use that. And then it's changes to 80 again. Otherwise, we'll have a huge sample size. So let's say I have, let's say there's 3 groups. Say I'm going to measure it 4 times. Okay. I'm going to allow a correlation, because if you measure once, a person that's scoring low on a test, they're going to continue to score low. They're not all of a sudden going to go up, probably. A person that's a high scorer probably going to remain kind of high. So let's say we have a medium correlation, say about a 0.3 between the groups, okay? And then I'll just leave this non-sphericity correction. This epsilon is 1. Again, that's about... I know about as much about this as I do about the non-centrality parameter. It's not really necessary unless you did have some kind of correction that you wanted. But if you leave, usually if you leave these kind of things at 1 or as the default, you're going to be okay. Okay. So I need a total sample size of 33. That's hardly anything at all, because the more repeated measures you have, the lower your sample size is going to get, because every repeated measure is almost like another sample that you pulled. Okay, so let's say if we only had 3 repeated measurements. Now it went up to 39. Not much difference. Say if I only had 2. I had 3 groups with 2 repeated measurements. Now I need 48. So not too bad. Yeah, so there's all kinds of different ones. Is a correlation among repeated measures for the same group? It would be yes, because basically you're saying the correlations for each person or each record, measurement to measurement. So basically you're saying correlations between. And how about the between factors? Between factors. Okay, let's look at that one. Let's see, do the 80 again. We had this, number of groups 2, number of measurements 4, and we had 3, right? Before. So let's calculate that. A little bit bigger, okay? Because now we're looking at between groups. So we're looking at over time between the groups. And then you also have where you can look between and within, and then the interactions. So you can see if there's something, are the groups change? Not only are the 3 groups changing, but are they also changing over time? Like say, does group 1 go up, down, and group 2 goes down, up, and maybe group 3 just stays steady, right? So they're all doing something different. So you're looking, are those groups, or is there an interaction? Are they doing different things over time? So we can try that. And now we're looking, say with the 3 groups, 4 measurements, and let's do our 342. So, it changes a little bit. So I would say then in general, looking at all these different ANOVAs, for the repeated measures, no matter if you want between, within, or the interaction, I would say if you got a sample size of say 80, you're going to be just fine, right? Because none of them are that high. And 80 might be overkill, but you want to account for attrition. Maybe people will drop out and you like to have complete records, right? So there's all these other things you kind of need to think about also, okay? Let's see, let's do correlations. So for correlations, we're going to use exact tests, okay? And then we're going to go in right here. It comes up right away, but you do have other options. You always have these different options, okay? So we have a lot of differences in proportions here, okay? But we want the bivariate normal model. And again, we want a priori. Let's do the two-tailed test, okay? So our sample sizes, again. Well, we know, I have this memorized. 0.1 is small, 0.3 is medium, 0.5 or greater is large, okay? So let's say we go for a medium correlation. So we have our 2 variables, and we want to see if there's an association between them. Is there association, say, between scores of marital satisfaction and happiness? I don't know, something like that. Okay, so you have satisfaction versus happiness. Okay, so we just want to see if there's any kind of association, and we want to at least be able to see a correlation of a moderate correlation of 0.3 or better, right? And if we set it at 0.3, anything at 0.3 or above, if we pull the sample size, we should be able to see that effect. Okay, so 80 again for our power. Okay, and we're going to set this correlation here for this is for your null hypothesis. So our null hypothesis is usually always saying there's no difference, there's no correlation, right? So correlation of 0 means no association, no correlation. Okay, so that's going to be where we set it. Okay, so we're going to compare versus if there's no correlation, is there a correlation of 0.3 or better? And we'll calculate it. And 84. I do this one so much that I have that memorized, that a correlation medium between 2 variables is going to be 84. So anytime I do a study where I know a correlation is needed, just this type of Pearson's correlation where it's 2 continuous variables, or a continuous versus dichotomous variable, those are also, or even 2 dichotomous variables also, they're all computed the same way. But if it's a Pearson's correlation, I know with a medium effect, it's going to be 84. Let's say I want to see maybe a stronger effect, right? 0.5. Only 29, right? Because you're going to have to see a big effect, So if you see a big effect, you don't. If they're that associated, you don't need as big of a sample. Let's say say I want to look for a very tiny association. Oh, I'm going to go with 0.15. 154. You put whatever number you want in there. Now I need, oh my gosh, now I need 328. So I need a huge sample because it's a small effect. Okay, so yeah, that it all changes. And then of course, if I want a one-tail test, one tail though, okay, maybe I want to see that small effect, but boy, I just want to see if the correlation is going in one direction. I just care if it's positive. Okay, instead of right now, when you have a two-tailed test, it's saying this 0.154 or better. It could be either a negative correlation where one variable is going up and the other one's going down, or it could be a positive correlation where they're both variables are moving in the same direction. Okay, so if I have a one-tailed test, I'm saying, oh, maybe I only care if they're positive. If they're negative, I don't really want to see a negative correlation. They should both be going in the same direction. So then I can calculate that. Now it says I need 259. Still big, but it's about 170 less, right? So yeah, it does change. So as you change the numbers, it's going to change. Looks like we have some questions. What does the number of measurements mean? Indu, I don't know, where was that number of measurements? Oh, you mean in the ANOVA? The number, yeah. The number of measurements is how many repeated measures. right? Are you taking them, like I said, the pre, post, and midterm? Maybe you have a clinical trial and you are testing them after 6 months of treatment, 1 year treatment, 2-year follow-up, 4-year follow-up, 5-year follow-up. So every follow-up time is a repeated measure. Okay. Okay. Any questions on the correlations? Those correlations I love those. Those are pretty easy. All right. I know, Indu, this is your favorite. You wanted a multiple regression. I remember when you wrote in, you said you wanted a multiple regression. So we're going to do that one next. Okay. So now we're going to go back to F-tests. Okay. Then we're going to go here and we are going to choose, we're going to do this one. Okay, this one right here, this fixed model R-squared increase, is when you have a hierarchical regression. So what that means is you're going to throw some variables in on one step, and then you're going to go up another step, and you're going to take those variables from the first step and then add even more on a second step. And you could keep going, right? You could go 3 steps, 4 steps. This will help you, GPower will help you up to 2 steps. And I'll show you that one right after this. But right now, it's just all your variables, all your predictors are going to be thrown in on one step, and you're going to look and see if they're significant on your outcome. Okay, so we're just going to do this one. Fixed model R-squared increase. Okay, and again, a priori. Okay, here's our effect sizes. Small is 0.02, medium is 0.15, 0.35 is large. Let's go with the medium, right? So we'll leave it like that. Our error's right where we want it, 0.05. And our power, let's do the 0.80 again, because we like that. Number of tested predictors. Oh, wait, I did the wrong one. I did the increase. Sorry about that. Okay, deviation from 0. This is for multiple regression. So 0.15, error. Don't you love watching me do this, figure this out? Okay, number of predictors. How many independent variables do you have for your regression? All right. And the more you have, the more of a sample size you're going to need, right? So let's see here, number of predictors. Let's say we have 3 predictors, okay? So we have a power there, 0.80, which is what we want. We want it to be more than that. Sample size we need is 77. So 77 will allow us to run a multiple regression, and we should be able to see a kind of a medium effect size if we use 3 predictors, okay? Let's say if we had 5 predictors. Need a bigger sample size, okay? And if you want to go crazy, if you're a data scientist, I have 100 predictors. That's not too bad, 338, Okay, but now I want to see a small effect. Let's say I want a 0.02, right? 0.025. Now I need a 1,600. That study, I mean, unless you're pulling records from some retrospective database or something like that, I really doubt you're going to want to go out and collect 1,600 records. So, and how many studies do you have? 100? Usually if you're going to have 100 predictors, you're not really testing hypotheses. You're doing some kind of exploratory study. You're just going in, you're data mining. You're trying to see what's out there that might be significant, and you'll have a lot of records. That's why I was saying this is data scientist territory. Where it's like, I got a huge bunch of records. I'm just going to mine it and see what I get. Right? What statisticians mostly, we like to have our hypothesis. What are we testing? We're looking for something, right? Let's see. What does the effect size mean in the linear regression? Well, there's computations. I would have to pull out the formula, but it's on the same principle. You're taking it's based on the correlation coefficient. It's basically a lot like that correlation coefficient formula I showed you, except now you have more than one predictor, okay? And it's all on one outcome. So you can determine an effect size too in your regression, okay? But what you need to do is you're going to say, well, I would like to have my predictors to be correlated, have a correlation of 0.3 or better, right? So you could put that right here. And it's going to calculate your effect size here, and you're going to transfer it over, okay? So it's like, how strong of an association are you going to want to see? Here you only need 171 to see this effect based on a correlation here, 0.3. Now, if I have it based on 0.1, now I'm going to transfer that over. See how small my effect is now? I'm going to calculate it. Now I need many, many more. So you can use your correlation coefficient, but it's based on, yes, it is like an adjusted R squared. Yes, Indu, it is. It's basically your R's and your R squared. Yeah. Let's try the hierarchical one where we have, maybe we're going to throw in 3 predictors on one step, maybe our controls. A lot of times you'll do a regression and you'll say, I'm really interested in if happiness and satisfaction, marital satisfaction go together. However, I want to control for some variables. I want to control for gender. I want to control for maybe race, ethnicity. Maybe I want to control for socioeconomic level, right? So those 3 things might have something to do with it too, but it's not my variable of interest. But I want to look at them. I want to include them in the model so I can control for those effects. And that's when you would do a hierarchical regression. So it's in the same area, except now we're going to look at an increase. So what we're going to want to do is build this so that we're going to say, let's say there will be 2 factors we're interested in, maybe satisfaction and time spent at the office, okay? Something like that. Those are our predictors we're interested in, and then our outcome is happiness. But we want to control for 3 demographics. Okay, so we're going to do the same thing. Maybe we'll have that small effect. The error here, we got the 0.8. So what we're going to do is we're going to have the number of tested predictors that we're interested in are 2, right? Those are the ones that we're going to put in on step 2, which are going to be our satisfaction and our hours worked. But our total number of predictors are going to be the 3 controls we put in, plus those other 2 on the second step. So we're going to have 5 predictors total, okay? Then we'll just calculate it. And we need 68 people altogether to do that kind of regression, okay? So that's a nice one too. Let's see, let's do, you guys want to do chi-squared? We can do chi-square. I think we have some time. Then we can ask some final questions. All right, this one's going to be more like a, okay, good, yay, Indu's excited, sure. This one is kind of based on a clinical kind of research, okay? We've been kind of talking about, regressions, things like this, but here's the problem, and I'm just going to read it off of my notes here. But it's known that a certain type of skin lesion is going to develop into cancer 30% of the time if patients aren't treated, okay? But there's a drug on the market right now, a current drug, and it's going to reduce the probability of getting cancer, of it developing to 20%. So that's like a 10% decrease. So everybody's happy about that drug. But a pharmaceutical company, they're developing a new drug. Okay, so they want to develop it to treat the skin lesions, but it's only going to be worthwhile to do so if the new drug reduces that probability to 15% or better, right? So 15%, or 10% or something like that. Because remember, it's the percentage of developing cancer, right? So if the current drug still allows for 20% of it happening, we want our new drug to make it 15% or maybe 10 or less, right? 10, 5, anything 15% or less of it happening. Okay, so the pharmaceutical company, they're planning a study, but they want to see if it's even feasible. So they're going to randomly assign patients to a treatment group and a control group. Okay, so the company wants to know how many subjects are going to be needed to test the difference in the proportions, with a difference in proportions of 0.15 with a power of 0.8, alpha 0.05. Okay, now this test here actually, since it's you have a treatment and a control, and then you have like improved versus not, it's like a 2x2 table, but you could do a test of proportions. You could do a chi-square test of independence. You could even do a simple logistic regression, and you're going to need the same. Either way you figure it, you'll need the same sample size. But I'm going to show you how to do it, and you do it, you'll figure it all like this. So what we can do here is, let me put my glasses on because I can't read these notes. Okay, so we're going to go to the z-test. And then we're going to go here, and we're going to go to test of proportions. Difference between 2 independent proportions, right down here. Okay, and a priori. Okay, and then we're going to have 2 tails. Now, really, we want improvement, but I'll show you the difference. Well, if we just have 2 tails, that's just like, is there a difference? But what we really want to know is if our treatment's going to be better, right? But for right now, let's do 2-tail test. So proportion 2 is the one that we want, which is going to be 15%. Proportion 1 is going to be 30. That's if there's no treatment, right? Because they're the controls. And our 80% power. And the allocation, we're going to have equal groups. Okay, we're going to allocate them equally. So we're going to calculate it. So we're going to need 242 people. Okay, and that's going to be equally divided. 121 in one group, 121 in the other. And yeah, it's good, but a two-sided test, really, it doesn't make much sense in this situation because we want to test for a drug that reduces the probability of cancer. So that's actually one test, right? We don't want it to increase it. We only want to test to see if it's going to reduce it, not make it worse. So we just maybe want to use the one-tailed test because it's going to say, right now it's 242. It'll save us some people, it'll save us time, it'll save us money. Now we only need 190. Yeah, we just shaved off 50 people. Okay, so that's much better. 95 per group. Okay, so that's it for that one. Let's see if we have any questions on any of these at all. Any questions on the power in general? I think we have some time. Okay, so Indu's asking a question. In linear regression, what if I wanted to split, let's see, the entire sample into training, test, and validation? Okay. So are you asking if that's going to make a difference on the sample size? How do I come up with the sample size for each split? Well, you would want to power it for whatever your test is. So at each split, you're going to, well, probably you're going to power it for your training set, right? That you're looking at. That's the one that's going to have your most predictors. Power it for that. That's a hard one because again, now we're going back into the exploratory, right? Or you're building a model. So typically you're going to have so much happening that you're going to be wanting to look at your effects. What I would probably do is when I ran that test, not just look at the significance, but I would also look at the coefficients. The regression coefficients to really see what is looking like there's some bigger values there, right? A regression coefficient of a 0.001, even if it's significant, is it something you really want in your model? Sometimes you might, but sometimes you might not. So that would be a little bit different. Jerry wants to know, for multiple groups, repeated measures, GPower asks about the correlation. Is this the correlation between all the groups over time? Let's see. And Indu has another, where can I get more information on various tests and how to set up the data for each of them? Oh, let me show you the PowerPoint again. Okay. Here's some references. The UCLA website is great. You can go to this IDRE, Institute for Research and Education. I think I put this on every single webinar I ever do. But it shows you step by step on all the different software, SAS, Stata, SPSS, I think even R. They'll show you, things like that. So you could actually go to that site, look up power analysis, and probably find any number of ways to run the power. And I'm sure they probably have GPower there also. That'll show you some different ones. The StatSoft site also shows how to perform power analysis with Statistica software if you have that. Some people do. This is a great GPower reference. There is actually a GPower manual that the authors of GPower put together, which is fine and it's great, but this is better. It's at this one, Mormons in Science, and I don't know really what Mormons in Science have to do with this at all, but let me see if I can click on it. My computer's running slow. So it's kind of strange looking. You go there and you go, okay, here's Back to the Future stuff. And but if you look down here, there's a whole table of contents with all the different things you can look at in GPower. And then you go down a little bit further, and there they are. And they tell you exactly what to plug in, where, and why. And there's even a couple videos. And the person that's been doing this actually has added some videos now, so I guess they are working on it some more, but they hadn't worked on it for a while. But my gosh, you have down here for your ANOVAs and such, the ones that you're asking all the different questions about the repeated measures and such, step by step. Here's a logistic regression if you have a dichotomous predictor. So this is a very, very nice one. So I would suggest that one for sure. And then there's an online text you can look up too. But I love this one, Mormons and Science. I still use this. I mean, there's some times where, I mean, I can't remember everything offhand. I mean, I had to use notes for this. The t-test, correlations, I can do piece of cake. But boy, when those ANOVAs or man-novas, I have to think about it. And then sometimes it's a little confusing because, you know, they're very cryptic, some statistical software. I mean, if you get an error message, sometimes it's like, what in the world does that even mean? So yeah, it's nice to have a little reference like that. Let's see. Barbara wants to look at 3 independent variables and 1 dependent variables for sample size for correlation. I think you might mean regression. Okay, so you have 3 independent and 1 dependent. So yeah, we could look at that. Let's see. So yeah. So let's go back in. Oh, that's that F test. So we're going to go down to the regression, deviation from 0. Medium effect size. What was it? Let's do 0.25. Okay. Error. And then we're going to have, how many predictors did you want? 3 predictors? 48 if you have an effect size of 0.25. Okay. Let's try the medium, 0.15. Now you need 77. Yeah. Another thing is too, there's a lot of rule of thumbs for sample size. If you just need to like eyeball or guesstimate, a rule of thumb for a multiple regression is that you need 10 records for every predictor. So if you have 3 predictors, you're going to need at least 30 records. Okay. I think that's a little small. Right here, it's saying for a medium effect size, you're going to need to have, 77, right? If we have a large effect size, which is I think was 0.35, now you're a little closer to your 10. Sometimes you read 20 per predictor, right? I think I would probably play it safe and do to 20. But if you type into Google rules of thumb for sample size, I know one everybody's heard of too is 30 for t-test, 30 per group, right? So if you have a sample size of 60, 30 per group, you should be good. Well, it depends on what size of effect you want to see. If you want to see a small effect, you better up that a little bit, right? Okay, so Jerry wants to know on the GPower graphs, which group is represented by the blue dotted line? This is actually, the blue dotted line is going to tell you your power. This is your power over here. This is your saying that you don't have significance when you really do here in the shaded. And this dotted blue line here is actually your sampling distribution. And this red line here is supposed to be your population distribution. Okay, so here we have something that kind of looks like a chi-square kind of thing because well, it's a one-sided test. Here's your F. What are we looking at? The linear regression. Okay, so right here would be your sampling distribution. And so that's just a representation of that according to the criterion put in. Let's see. Oh, Indu had a question from above. Setting up data for various statistical tests. Okay, setting up data for various statistics so I can come up with the sample size. I mean the format of the data. Do you mean like, is it continuous data or dichotomous, or I'm not sure what you mean by the format. Like, should they be long or what? Oh, no, you don't need to worry about that, the data. But I mean, you don't have the data here. We're just putting in numbers in GPower. You don't have the data set up. You haven't even collected your data yet, right? And then, yes, depending on the test you use, sometimes you would need wide, sometimes you would need long. And it also doesn't depend just on the test, but on the software you're using, okay? A lot of times, like Stata, longitudinal needs long format, but some softwares might want it in wide. I know SPSS, for some repeated measures, you have it in a wide format. And other repeated measures like the linear, like the longitudinal, you have it in a long format. They're both over time, but depending on what test you're using in the software, it really depends on that. Is there literature around this? I mean, as far as well, it depends on the software you're using. So I would use check the help on the software to see what they're saying, how you should enter that. Yeah. Depends. It depends on the test and do. They're all different. And so I would need to know what kind of test it was, and I would probably have to look it up myself to see if it goes wide or long. Yeah, but it really depends. Yeah, and I know that's Paul's favorite thing for me to say is it depends. But statisticians say that all the time because it's not. I wish it was that easy where it was just a cut and dry answer for a question. But it really does depend on what your research questions are, what effect you're looking for, what you're testing, what kind of test you're using, what kind of software you're using. Sometimes there are some rules that are hard and fast, but it's amazing how many rules can be relaxed or changed depending on what you're looking at and what you're doing. Yeah, and it just comes with practice. It's like being a doctor. You come out of school and you have to look everything up, and then as you go along, you get a feel for things. Or a pianist, right? You start playing, you have to look and you have to practice your music, and but after a while you memorize things and you can read music like a breeze, right? So it's the same thing with any kind of work you do. That's right, Indu. It's never cut and dry in stats. She's absolutely right. Okay, so do we have any other questions? You can always type yes, so I know it's coming. Okay, let's see. If you have two styles that Henry's asking, if you have two styles of a practice and a control group and one dependent variables, do you have two IVs or one IV with two levels? Is ANOVA best? Okay, so you have two styles of practice and so you actually will have three groups because you have one style of practice, a second style of practice, and a control group. So you actually have three groups, okay? Because you're going to have to compare them to a control. Right. So even though it's a control, it's still something that you need to compare the other two groups to. Right. So it would be an ANOVA. You're absolutely right. And because it has one dependent variable. If you had more than one dependent variable, then you have MANOVA. Okay, which is multivariate analysis of variance. Okay, so but yeah, one dependent variable, ANOVA if you have more than two groups. Okay, we have about 5 more minutes if we have any more questions. Well, this is great. I'm so happy everybody came and is asking the questions. Let's see. When will we get to presentation? That's a good question. Uh, you should get it probably over the weekend. I do the stats grab bag now. I don't know if you guys have seen that. If you're on the mailing list, if you signed up for this webinar and you're not on my mailing list yet, I will put you on my mailing list, and you will get a monthly newsletter. You'll get announcements about the webinars that are always free. You're also going to get a stats grab bag every week, and that's basically things that I do because I'm a practicing statistician. So I thought it would be kind of fun to every week send out something that I was working on that week. Not the actual work because it's usually proprietary, but maybe something I came across, so that you might find interesting. I think what was a couple weeks ago, that was MANOVA. I think last week it was like, I had some problems with my calculator, how I fixed that, and then a couple other, how to clean your data up nicely. And I'll send links, references, and things like that. So probably you'll have it by Monday because I'll probably work on this at the same time I do that grab bag. Let's see. How about plotting X and Y for a range of values? Yes, I'm not sure about that, Jerry, what you're asking on that. How about plotting X and Y for a range of values? That'd be a correlation, it sounds like, that you're talking about. On GPower at the bottom. Okay. Let's look at this. Oh, I haven't used this in a long time. So what it does is it'll give you the range of values at different power. So what we're going to do here is we're going to draw the plot. Okay. So we did this linear regression, right? And we did the 3 predictors, and we had the error probability of 5, and the effect size was large. So what we can do here is what it does is it gives you a nice little plot. So if you say, well, gosh, the sample size at 80, at a power of 80, we need about 35, right? But say, gosh, I can't get 35 people. I can only get 20. Well, what you can do is you can go down. Well, okay, this doesn't go down that low. See, I can't get 35 people. I can only get 30, right? So you'll go, okay, here's 30 people. With 30 people, I will get about a little bit over 70% power. Okay, so it kind of tells you, it's kind of gives you, this is like where I was saying where the statistician will give you a range of values, and then you can kind of go, all right, well, I think with all I have, this will be the best number. Say if I had 50 people, if I was able to get 50 people with this criteria, 3 predictors, a large effect size, and I had 50 people, my power would be really, really high. It'd be almost 95%, right? So that's what this does. Indu asked if I have a website, and I do have a website, and it's right here, www.omegastatistics.com. You can read all about me, and I think the webinars are all up there, and this will be posted up there too. And you'll also get a copy of the handouts and everything, and I'll let you know when it's posted. Okay, well, I guess we're almost done. You can always email me if you still have questions. Eventually, I'm trying to get a forum together of some kind so that we can have like a Q&A board. And then if you have questions, you can come and ask, and I'll do my best to answer them. And I'm making I have big plans, I have a big vision. But like I said, I'm a practicing statistician, so I try to get it done as soon as I can and try to work on projects too. But I thank you all very much for coming. I really enjoyed this. I hope you did too. And I see many people thought it was very helpful, which makes my heart happy. And have a great rest of the day, everybody. Bye bye.